So here's the next stream. We'll see how it goes. So last time, which is days ago, we tried to do a 5x5 kernel in HLS. Let's see, pop that up real quick. Or I think I might convert it back to the 3x3. And we tried to do a 3x3 and it didn't fit. And I tried to play around with the parameters. The best I could get was this, where we're 386 LUTs off from fitting inside the FPGA. And looking at the utilization, I don't think there's much we can remove unless we want to like just straight up remove the microblades or something, but we need that to run the code. I bet the axis interconnect's a little bloated, but I don't think there's much we can do about that in this situation. Maybe we focused on DDR only being accessible from the from a different connect, like the microblades would just drive the peripherals, and then the VDM would have exclusive access to the DDR. That might work, but I think I decided we're gonna do a VHDL implementation or hardware implementation of the design. So we open up this. Let's see if this is a 3x3 or 5x5 version. Pretty sure I changed it back to the 3x3. Never changed it back to the 3x3. Do I not have that? Oh. Looks like I might have got rid of it and not replaced it here. Well, that's fun. Guess we could try to fix it sometime, but I'm not really in the mood to try to fix it at the moment. I should really get the 3x3 one and submit it to get a GitHub for it and whatnot. Okay, yeah, let's just convert it back real quick. It should be fairly easy. Okay, going down. Make that 9. 9. 3x3. And make that 3. 3. 3. 6. 7. 5. 4. 5. 4. 5. 8. Okay, 3x3. Commented junk. It's all good. I'm just gonna have by 3. Okay. One. So we need to implement this in VHDL, which will be an interesting challenge. Say the least. those two, those two. That. Okay. So if one is there, 0, 2. 2, 2, 0. Zero there, one there, two there, two there. We're just gonna set this back. So hopefully, good. Go. 0, 1, 2, 2, 2, 2. And we should almost be done. We just open the H file after this. Should be good. And then at the bottom, we define a window as a 5 by 5. We're going to divide it as a 2 by, oh no, 3 by 3. Do this. Maybe I'll have this rebuild while we're waiting. Errors. Yeah, so the 5 by 5 didn't work. We're gonna have to do an HDL design, and I'm gonna demonstrate what I've been thinking about. We'll see how it goes. Probably get out PowerPoint and talk about it. Okay, it looks good. Let's package it up. Yep. Yep, we're good. So we're gonna go to open block diagrams, refresh IP catalog, add it, rebuild it, make sure it works because in all honesty, we've changed around a few things. Fresh IP catalog, upgrade selected. Okay, we'll skip that for now because it'll just rerun it. So yeah, just go ahead and generate a bitstream off it. So let's talk about how we want to do this. So besides having a good drawing tool, let us use we just use paint, or let's just do this. I can just set that to the side and talk about the resources we need. So insert some shapes. So we're gonna need line buffers. Buffer 0, and we're gonna have to go to line buffer n, right? So I want to make the VHDL parameterizable, and then we're gonna have a table, right? Fine. I don't think. Sure. So we have a 3 by 3 table, and it's going to be 1 or 0 dot n dot n. 1 or 2 or something like that. And then we have coefficients for each of these values. So what we want to do is then convert it into a table that's going to be 1 by 9. We're going to have to pipeline this. So this is going to be the zero value of this times the coefficient. right? Well, I wish that spaced out better. Wish I could just double click that. Okay, we have basically n squared. Let's see what Vivado is angry about. That's okay. You're right. Sense design. So, and then we need to do n squared times r. So what we want to do is we have this multiplication, right? We have a 8-bit signed value that we're trying to determine, and we're going to want to do it kind of stage by stage. I should just do this in Excel. I feel like Excel would be. Yeah, I feel like this Excel is going to be a better representation. Let's open this in Excel. Excel. Blank document. Okay, so we're going to need. Going to merge and center. Line buffer 0. Line buffer n. And so start right here. So we have a 3x3 matrix, right? Going to this is going to be 0 to n squared, right? So we're going to have different stages. So our first stage is going to be coefficient 0, and then coefficient 1. And let's see if I can just do this all the way to coefficient 8. So we're going to try to simplify the math here and get good timing of it. This is actually the sign bit. Sign. So using the magnitude of the coefficients, we're going to take this is kernel K, or no, this is our window, and the C is actually kernel. Probably better to have K, but whatever. Coefficient, our kernel. So we're going to take window 0, and we're going to shift it over by 0 if this coefficient is high. If high. And we're basically going to do that all the way to n squared. And then for this one, what we want to do is we're going to take this, we're going to take coefficient window 1, and we're going to shift it over 1, and then we're going to plus equal to our rolling sum. W, or we'll just call it sum. Add to sum. Right. And we're going to do this all the way to here. And what this should do, oh, and W, this should be a 16-bit sum as well. And once we continually add it to sum, we should have a value. And then we just need to change to negative. at this last stage right here of doing the coefficient. So this is how many stages or the latency of our system is going to be. And we don't have to use any DSP, so this is going to have no DSPs, which is going to be great. Do that for this thing. And now comes the fun step. We need to sum it together. So we have n squared values to sum. And this is where it gets tricky. I mean, we could try to do it as pipeline stages and for loops and stuff like that based upon the value. But okay, so we have 9 values of sum. We want to make kind of a summation tree, or we could do a fancy summing tree, which would be a good review of my arithmetic class. So I might have to look up how to do a summing tree, and we can maybe do a summing tree here. That'd be a fun review of my arithmetic class, where we can just add all the bits up first and worry about the carry bit later, in a way. Maybe pipeline it a little bit. But yeah, we need to have some stages here where we could kind of pipeline. We could just add 2 values together, 3 values together, or something like that, and do it in stages. So we have, in this, let's say we have 4 sum stages. Eight, 7, 8, 9, 10. So we're looking at probably 12 cycle, probably a 13 cycle latency to get this up to date, push it over, or something like that. So we'll say that's 1 cycle right there. So we sum it. Now we have a few things to consider. There's a shift value where we take the summation, and we shift it over by a specified value, say m. And then we have a lower bound and upper bound. And this is just like, what's the lowest color, what's the highest color it can be. That kind of bound it out a little bit. And then we're good, and then we just have to export the data. So we look at this, right? We're talking 14, 15, 16, 17, 18, 20. We'll give it 20 cycles of latency. So we can potentially solve this with 20 cycles. So let's look at HLS. HLS is giving us a minimum of 40 cycles. So it's not as quick as possible. So just theoretically, we can make our VHDL much faster than HLS. Resource wise, so look at this, DSPs. It is using 17 DSPs. Let's see if our bit file finished. It did. So if we go look at here, right, we're using 28 DSPs. Let's go look at what that could potentially mean. So let's open up implement design, and I think we can use 0 DSPs here. And we can also parameterize it that the latency may increase. This may be depending upon how we can do our addition tree of a set amount of values. But we could potentially add that into a block structure where it increases the amount of stages that exist. That'd be an interesting thing to have kind of variable latency based upon the parameter of the kernel. So yeah, I think we could probably have 20 cycles definitely could have a good 20 cycles for a 3x3, and then we could do something else. So okay, one thing we did not talk about was the grayscale feature here. We have a grayscale option, at least in here. And the grayscale they use is times 66 times 129 times 25 plus the 128 shifted over by 8 plus 16. Yeah, I think we can implement that without a DSP. That'd be really interesting. So to see filter operator, how many DSPs are we using? Using 28 DSPs just by itself. I think we can make it better. 1200. So it's gonna be interesting what what the version of this will be. Do we want to do grayscale at the end or grayscale at the beginning? I gotta say the grayscale at the beginning was not what I expected. I feel like we want a grayscale at the end. Make it optional. Give it like an optional another what 20 cycles it could take potentially because the way the grayscale works. To me, well, we're not too worried about timing at the frequency we're doing it, so we'll probably just ignore the grayscale at first. And people can implement the grayscale using using, can they? I don't think they can do a grayscale. Kernels consider guided by colors. So we'll probably try this with grayscaled images first, or just one color, and go from there. Like we'll just do red or blue or green first, and ignore the other colors, and just prove that it works. And then we can just copy and paste it for the 3 other colors, and then look at maybe doing a grayscale at the end. Maybe I'll add a quick register that changes it. Okay, so the register functionality. I think we're just probably going to have to do 5 registers. So we're gonna have the shift value. We'll play at the grayscale. At some place, shift value, lower, upper, and then kernel index, and then kernel value. So by doing this 2 level to right to the index, we then could have an easy way to parameterize it so that it could be a very large kernel if need be. We can push the bounds to see how far we can get with our little system. Okay. Anything, let's just check, make sure this bitstream works. So let's go ahead and open up launch the SDK. Feed. I'm going to load this bitstream. I played around with some stuff. I just want to make sure the timing wasn't affected. 4% got down. Good. So we're going to open up hardware. Oh, let me go pause my other experiments that I have running. Okay, pause that experiment. Oh, I should probably get my camera up and running just to verify that this works. Okay. Getting the camera set up. Let's see. So we're going to turn on the Droid camera. Okay, let's see how you guys see it. Turn on Droid camera. That for now. I'll bring over the Droid camera vision thing over here so we can keep track of it. There. Okay, let's program the device. Program that. Yeah, that's the right one. And then we're going to go to the SDK, go to runtime configurations because I'm pretty sure this one programs to the old one, and hit run. So we should have our little. Sure, it's not going crazy. Okay. So looks good. Let's load in an image real quick. C stream the image proc. That targets. I want to target. Where do I target? DAO data test 000 bin. I'll put that into the DDR 154. Okay, cool. So we have it working. We took away a bunch of stuff, but it seems to be working well right now. So I think we're probably going to stop the stream here. We've kind of discussed what we're going to do in HDL, but HDL is going to be a little bit more complicated than what we hope to do. So, I mean, we want to create an IP. Does that. Sum this all together. Not sure how we want to do that summation tree. We just want to do a huge sum, not worry about the values. Or we want to do a addition tree of some type. I have to think. I think I should probably review my arithmetic. We'll think about that. We could probably do a quick sum tree, see what happens. We probably should be able to do it at our given clock rate, and these things should be easy enough. So the hardest thing is going to get this parameterizable. Especially for the line buffers and the window, which is just 3 shift registers. Shift registers, and they're shifting. So it's, oh, how is it shifting? I think we had it. Yeah, so the newest value come here and they shift this direction. And all 9 values are used for the first for the shifting thing. So we would have to store them, pass them along. Which sounds interesting, to pipeline that completely. But I think we can do it. Okay, well, I think we're just going to pause there for now. We'll look at the hardware later. Maybe I can review some arithmetic adding trees for FPGAs. And we can do something elegant or efficient. We didn't have any live viewers, so I thought, okay, feel free to join us next time. And goodbye.